Today we are going to discuss no load and full load condition. This is quite important for our examination. Now we have already discussed what do you mean by no load or full load, right? So what happens when there is no load on the transformer? Now what is the meaning of load? Anything which is connected at the output. Now no load condition means that nothing is connected at the output, means it is open circuited. And full load means that we are going to connect full load at the secondary. Okay. So let us first discuss no load condition. Now what is the meaning of no load? Meaning of no load is we are not connecting anything in the secondary winding. It means it is open circuited, right? Now whenever a circuit is open circuited, what is the current? The current will be zero. So the secondary current in this condition will be zero. Now since the secondary current is zero, here a small current I0 flows through the primary, and this current is known as no load current and it is represented by I0. Please remember that generally primary current is represented by I1, but that is under normal condition, but here we are specifying no load condition. So that 0 in I0 represents no load condition. Fine, this is actually primary current only, which was earlier represented by I1, but because of the no load condition we are representing the same current as I0. Okay, and this is going to be very small current. Essentially it is going to be only 2 to 10% of the rated current. Okay, so here we have two functions of input primary current. It means what job it does. So it basically supplies the iron loss, which is nothing but the hysteresis and eddy current loss, and it gives very small amount of copper loss. Now why I said very small amount of copper loss? Because copper loss is proportional to current and here current is very small. So basically under no load condition, whatever loss is there, it will be representing iron loss because copper loss will be very less in this condition. So the circuit diagram is shown here. You can see that output is open circuited, so I2 is 0 and a small current I0 flows in the primary circuit. Fine. Now this is the phasor diagram. Now let us talk about the phasor diagram. Okay. Now see, under ideal condition, our winding is pure winding, correct? But then practical condition says that it cannot be pure, so it has some winding resistance. It means, see, ideally our resulting current, which is I0, will lag the current, will lag the voltage by 90 degree, right? So see, what I'll do is, yes, now it is okay. So see, this was flux, okay? This flux will lag the input voltage because it is in the opposition, it will try to oppose. So it will lag, the flux will lag input voltage by 90 degree, fine. Now if this winding is ideal winding, then we should get I0 here, 90 degree lagging. But now this is not ideal, correct? It means that we will not get I0 here. So where will we get I0? Where will we get I0? It will have some phase angle which is smaller than 90 degree. Correct? Yes. Now this I0 has two components. Okay? This I0 has two components. That is the working component and magnetizing component. In some book it is also represented by I mu. Now remember we have discussed about magnetizing component. Magnetizing component is basically responsible for generating the flux in the circuit. Okay, so now this, if it is responsible for generation of the flux, It means this will be in phase, correct? And the working component will be here, correct? Now when you take the resultant, here is my I0. Okay, now this phase angle is nothing but phi 0, and it is very clear that it is smaller than 90 degree. Ideally it should be 90 degree, but it is not. Got it? Now please understand that IM is here vertical component and IW becomes the horizontal component. Why? Because phi 0 is making angle with V1. Okay, it is making angle with V1, which is at y-axis. Okay, so this becomes the base and this becomes the perpendicular. So let us see how do we represent IW and IM. Okay, yes. So this working component is represented by I0 cos phi 0. Remember I told you that IW for that becomes a horizontal component with respect to V1, of course. Then IM is I0 sin phi 0. So the resultant of these two will be this. Okay. Yes. Then we have the power factor, which is cos phi 0, and that is given by IW by I0. And this is the no load power input. Now this no load power input is V1 I0 cos phi 0. Now this is nothing sorry. Now this is nothing but the iron loss component. See, in the beginning we discussed that since the current is very small, the copper loss component will be very small. Okay, so whatever power input is developed, that is approximately equal to the iron loss component. I'll repeat, the copper loss component is very small, negligible, because the current is very small and copper loss depends on the current. So whatever power is getting developed, this power represents iron loss component. So please remember this equation. This is going to be very important for problem solving. Fine. Let us see what happens under load condition. So what we are doing is we are connecting some kind of load. Now that load can be resistive, inductive, capacitive, whatever. It depends on our application also. Okay. But since now we have connected the load, this is no more an open circuit, right? It means the current starts flowing. Now when the current starts flowing, see, this is nothing is connected, and here we have connected the load. Now when the load is connected, current I2 starts flowing. Now when this starts flowing, it sets up its own flux, isn't it? Whenever alternating current flows through winding, it sets up its own flux, correct? Now let us talk about this magnitude of I2 or the phase relation of I2. All this depends on the type of the load, correct? The phase between I2 and V2 will depend on the type of the load, and the magnitude will depend on the voltage and the impedance. Fine? Correct? Yes. Now see, you need to understand, I shall draw one circuit here and I'll explain it to you. Now suppose this is the transformer. Okay? Yes. Now here we had secondary. We have I2 here. Okay? In the beginning because of the input voltage, we got the flux which is phi. Fine. But this I2, when it flows through this transformer core, it sets up its own flux, which is phi 1 dash. And this phi was flowing in this direction. Okay. Now this will oppose the cause. So this phi 1 dash will flow in the opposite direction. Okay. Now here we have E2. Here we have E1 and V1. Correct? Now since this phi 1 is flowing in the opposite direction, it tries to reduce the main flux phi. Because both are in opposite direction. So currently what is the total flux? Phi minus phi 1 dash. Okay. So it tries to reduce the flux phi. When it reduces flux phi, it means it actually reduces E1 also. So this phi 1 dash tries to reduce E1. And for some time what happens is this E1 for some time becomes smaller than V1. Fine. Now when this E1 becomes smaller, or in other words V1 becomes greater, again its current starts flowing. Why? Because of the potential difference. See, under normal condition, E1 is almost same as V1. So there is no potential difference. So no additional current flows. But because of this special condition here, there is a potential difference. Now whenever we have potential difference, the current starts flowing. So now some additional current starts flowing, and this current is I1 dash. Okay, fine. Now earlier we had a current called I0. Now you can very well understand that both these currents are flowing in the same direction. Correct? Yes. Now this I1 dash is in phase opposition with this I2. Got it? Yes. Again what happens is this I1 dash is flowing through this circuit, and this also sets up a flux. Now this flux will oppose this phi 1. See this condition. Again these two are in opposite direction and they also oppose each other. Or in other words, they cancel out each other. Okay, so these two get cancelled. So what happens after this? After this, E1 again becomes equal to V1. Or what is the total flux in the circuit? Now it is phi, which was originally, moving through the core. Understood? So see, lot many things are happening in the circuit, but some kind of counterbalancing effect is there, and because of that, the final condition remains the same. Got it? Yes? So many things happen, but then this primary counterbalancing current nullified the effect of this I1 dash. Got it? Yes. Now this additional current which was flowing was I1 dash, and this was due to MMF N1 I1 dash. Okay. So this is how it can be represented. So finally we get the magnitude of I1 dash, which is equal to K into I2. Fine. Got it? So before going to this phasor diagram, please understand that essentially, again I repeat, this is very important. Now see, whatever EMF was getting developed, it was now same as the input voltage applied. So it means that, see, whether you are applying the load, whether you are not applying the load, it is not making any difference. So actually see, it is making a lot of difference, but then the effects are getting nullified. So at the end, there is no effect. Okay? At the end, there is no effect. Fine? Okay? Now let us talk about the phasor diagram. Now, how to draw the phasor diagram? Before going to the exact phasor diagram, we will try to learn how to draw the phasor diagram. So the very first thing is we will draw flux, which is phi. Okay? Correct? Now this flux sets up the induced EMF, which is E1. Right? And this will lag the flux by 90 degree. Now this E1 will be same as E2. I'm talking about the resistive condition, okay, when the load is resistive. So all these are same. E1 is equal to E2 is equal to V2. Fine? Okay. Now V1 will be in phase opposition to V2, or V2 is in phase opposition to V1. So this is exactly in the opposite direction. Correct? Now since the load is resistive, the current will be in phase. So I2 is in phase with V2. So somewhere here is I2. Now to this I2 we have the opposite current which was flowing. Correct? This I2 made the current to flow in the primary, which we represented as I1 dash. Right? And there was some current flowing which was no load condition. So this was I0, which is small. So this parallel lines have to be drawn, and this is the resultant current. Okay, which is now I1. Got it? So basically I1 is the resultant of I0 and I1 dash. Fine? Yes. Now let me tell you where is the phase angle. This is our phase angle phi 1. Correct? And here phi 2 is 0. Why it is 0? Because resistive load is connected. Got it? So this is how the phasor diagram is drawn. Now I'll explain what happens when inductive load is connected. So you have again phi. Okay. Now after this, I'm using different colors just to make you understand. Okay. So here again E1 same as E2, same as V2. But now the load is inductive. Okay. But remember, this is not pure inductive load. Okay, this is not pure inductive load. It means the current will lag the voltage, but it will not lag by 90 degree. So here is my current I2, which is lagging the voltage by phi 2. Okay? Yes. Now exactly opposite we have I1 dash, correct? And opposite to V2, we have V1. Yes, this is V1. Now I1 was already flowing, correct? So here, sorry, I0. I0 was already flowing. So here we have I0. So now resultant. So we have to draw the parallel line, isn't it? Yes. So this is the resultant current I1 and this is the phase angle phi 1. Got it? Understood? So this is how inductive load phasor diagram is drawn. Now what will happen during capacitive load? This will lead. So it comes here. And this whole portion comes here. Because this is going to be exactly in opposite direction. Fine. So let us see how it looks like. So see. This is how it looks like. So as I told you, in case of capacitor, it leads, so it comes to right hand side. Opposite to this we have here, actually I2 dash is there. In our case it is I1 dash. Okay. So I hope you understood this. Fine. Yes. So now let us take the winding resistance and the leakage resistance and then we will draw the phasor diagram. So see here we have considered everything and now we will try to draw the phasor diagram. Okay, everything remains the same, don't worry about it. Okay, we have considered the leakage reactance and winding resistance also. So this is how actually the circuit looks like, but it is represented as equivalent circuit, which we will discuss in the coming lectures. Okay, don't worry about that. As of now, you can remember that this is how the circuit looks like. So it has many components, right? It has R1, X1 towards the primary, it has R2, X2 towards the secondary, X1, X2 represent leakage reactance, R1, R2 represent winding resistance, and here we have the effect of input current, which is I0. It has two components, correct? Yes. So when this current I1 flows, we have whenever the current flows through a circuit, some voltage is dropped, correct? Yes. So now, see. Now here you have E1, right? So when we apply KVL, rather, wait. When we apply KVL here, what do we get? So the same equation is written here. Okay. It was basically, we are considering winding resistance, right? So it was basically V1 is equal to E1 plus I1 R1. So this equation has been converted into E1. So it becomes V1 minus I1 R1. Similarly, we have in the secondary circuit, we will have E2 is equal to V2 plus I2 R2. Right? So V2 becomes E2 minus I2 R2. This was when only winding resistance was considered. Now we are considering fictitious reactance also due to leakage, right? So here we get additional term which is minus jx1 into I1. Remember, this is a reactance, so it is going to be imaginary, so minus will come and the voltage drop will be I1 x1. So similarly, the same equation for V2 is also considered after considering the reactance. Remember, these are fictitious Reactances means they are not actually connected. Okay, they are not physically there, but they are representing leakage and winding resistances. Okay, so this is how the phasor diagram looks like. Fine. So again, how to draw this phasor diagram? So for that, I will go back and I will explain you one phasor diagram. Okay. So first, we will draw V2. Okay. Now, sorry. Now here you have phi. Okay. Here you had E2, which is equal to E1. This is resistive load. Fine. When the load is resistive. So E1 is same as E2. But now V2 will not be same. Okay, fine. Basically what happens is, first, actually we shouldn't draw. Let me take a reference here. Yes, otherwise it would be very difficult for me to draw. Yes, correct. Now it is okay. Okay, now I will draw V2. Now see, V2 will not come on y-axis directly, because now here we have winding resistance and leakage reactance also. Fine. So V2 goes here now. So now here is my V2. Okay. Smaller to this, I2 flows. Now why I2 is in the same phase? Because it is a resistive load. Fine. The load is resistive. Okay. Yes. So due to the winding resistance, I have one additional parameter which is called I2R2. Okay, I have this. Now I have one more component because of the reactance, which is yes, which is in phase opposition, not exactly phase opposition, which is 90° out of phase. So this is I2X2. What is I2X2? The drop across leakage reactance. Okay, so the resultant of this is E2, which is nothing but E1. Got it? So this is how we get E2 and E1. Okay, now opposite to this we have minus E1. Okay, minus E1. Now to this we will add I1R1. To that we will have I1X1. Okay, and the resultant of this will be V1. Okay, understood? Yes. Now the phasor diagram is not complete. Fine. Okay, so we want more colors. So opposite to this I2, I will have, what will I have? I2 dash. Okay, and then I have I0. Again, the resultant of these two will give me I1. Fine. And this is the phase angle. I'll write it here, otherwise it will be very complicated. Phi 0. Fine. So this is how the phasor diagram looks like. of resistive load. Okay. Now in this case we will take reactive load, say capacitance. Okay. So see, again we will have phi. Okay. After this, let me again draw some reference point. Yes. So here we will have V2 and the current leads, correct? So here I have I2. Now to this V2, here is V2. To this V2, I will add I2R2, correct? And then I will have I2X2 and this reference line. Actually it was not there, but I simply drew it for my reference. So this becomes E2, which is equal to E1. So here I will have minus E1, correct? To this I will add I1R1. Again I will add I1X1 and the resultant will be V1. Fine. Again this is not complete. We have to draw I2 dash and I0. So this I2 will have opposite I2 dash. Here we have say I0. So the resultant of these two will give me I1. And the phase angle between I1 and V1 will be phi 0. Okay. So this is how the phasor diagram is drawn. So in the last case, we drew the phasor diagram for inductive, and here we drew the phasor diagram for capacitive. Now you can very well understand for inductive, isn't it? So this is how it looks like. Okay, fine. So I hope now this topic is quite clear to you. Please go through this once again so that it is quite clear in your mind. We shall meet in the next lecture. Till then, bye-bye.